Yeah, comes on everyone. Let's start off. Hope everyone has tried the homework problem. Let's see. Find the magnetic pressure at a distance x. There, so we found the field as a function of x. So what we do? At a distance x from center, choose a thin rod. You're getting it is something like this. Meaning, if I just draw this a side view, I am exaggerating this again. This is how it would look. Where this length would be r d theta, this length would be dx, and this would be length L. Making sense? So on this small piece, we have a current I. Current I is flowing like this, where I is nothing but J into that area, which is this is XD theta. So this small length was D theta ka small piece. So the current in that section is J into XD theta into DX. That is the current in that small section. And how is the magnetic field? The magnetic field on this section will be this way, B bar. Because remember, the magnetic field lines are going in a circular like this. So this is your B bar. That means this thin rod is experiencing a magnetic force due to the magnetic field B. Is that making sense? So if you find the small force dF on this, which is I, dl is anyway, the perpendicular vertical, and B, so force is ILB. So current here is J into x into d theta dx, that is your current. L is the length, and the magnetic field is this guy which we derived, mu naught Ix by 2 pi r square. This is the force acting on the small rod. Now what is the pressure? Now remember, pressure is force acting on a perpendicular area. How is your force acting? Now the current was this way, the magnetic field was this way. So IL cross B, the force was actually acting this way on this perpendicular to this surface here. This is dF. So we need to take this area. You can't take any area you want. So the pressure acting on this surface would be dF by that area, which is L into xd theta. Because this was xd theta and this was length L. So substitute here. How much is this? This would be basically L is gone, xd theta is gone. So you'll be left out with J d theta dx mu naught I x by 2 pi r square. Theta is also gone. Yep. J into dx into mu naught I x by 2 pi r square. So, and generally we know how we take the pressure. We take the pressure to be this is P into area. This would be P plus dP into area. The difference is pressure. So you'll get a minus sign. That is a mathematical convention. We always assume the pressure is increasing with x. And then you're done. So integral dP mu naught J I by 2 pi r square integral x dx. When you take the pressure is, remember, you should take this as r because the pressure is 0 on the outermost surface. Be careful with the limits. Pressure is 0 on outer surface. There is nothing to apply pressure on the outer surface. It's a free end. That is x is equal to r. Do you remember that? We did the same thing even when we did for a solid sphere. The pressure is 0 on the outer surface. There is no one to apply pressure on it. As you go inside, the pressure will increase. So limits will go from x. So we will come with P is equal to mu naught J by 2. Now remember, I by pi r square is another J. So that becomes J square. And this becomes r square minus x square by 2. That's your answer. Mu naught J square by 4 r square minus x square. Have a look at that. So somewhere in the middle, take a small piece. Idea was the same. If you remember in electrostatics, we did the same thing. We took a small piece. Then we said the tension is T plus dt, T, and then we said force is EQ. From there, we found the dt, and then we got the pressure, and we did the same thing. Pressure on the outer surface is 0 because free ends have no pressure. There's no one to push. The only catch here is the element is a rod. Do have a look at this. You can't get. That is because you didn't read the statement we wrote. Read this statement. Ampere law is useful to find B bar due to symmetrical charge distribution. A finite wire is not a symmetrical charge distribution. They can't. You won't be able, the B won't come out of the integral. All clear with this? There, that is your pressure. Mu naught J square, R square minus X square. Let's see one more. We have an infinite cylinder, solid. This is R. The current density J is given by J naught into 1 minus X by R. Meaning when X is equal to 0, current is maximum, and as you go out, the field decreases, current decreases. Plot magnetic field versus X graph. X is the distance from center. This is the current density. Now here, even though this is non-uniform, there is a symmetry. Cylindrical, right? For a given cylinder, the current flowing is same. So there is a symmetry along the coaxial lines. When I say symmetrical charge distribution, it doesn't mean you should have constant. Should have there's some kind of symmetry should be there. Let's give it a try. How to do this? Same thing we did for the solid thing. At a distance x, take an ampere loop. Integral b dot dl is equal to mu naught into current. A V-shaped graph. Let's see. Do you guys remember this result? In a Gauss law, if the charge density rho is equal to rho naught into r power n, then the field is proportional to r power n plus 1. Don't forget that. So here the current density J naught is equal to J is equal to J naught x. Field also will be x power x square. It will be n plus 1. But this is 1 minus x by r. Let's see, will it be any different? Someone got mu naught j x square, x by 2 minus x square by 3. Okay, let's see. So consider a Gaussian surface at a distance x. So for x less than r, integral b dot dl. Now, if you see that entire green circle looks symmetrical about the center, so b must be same. Is equal to mu naught into I crossing. Now, what is the I in this? Now, in that green region up to x, again, we will take a small r, which is a small piece here. You have to integrate in that again. So at a distance r, take a small dr. This was a ring inside the x. So the current in this ring, I, would be integral j naught into 1 minus x by small r by r into 2 pi small r dr. The thin ring ka area is 2 pi r dr, and the current density is j, 2 pi r dr. This will go from 0 to x. So this small I will give you current up to x. This will be 2 pi j naught integral r dr minus r square dr by capital R. This will go from 0 to x. This is 2 pi j naught x square by 2 minus x cube by 3r. This is a current as function of x, everyone. This much current is flowing up to distance x. So this will be b into 2 pi x is equal to mu naught 2 pi j naught x square by 2 minus x cube by 3.
By 3.
By 3r. No? 2 pi will go off. 1 x also will go off. So field will be mu naught j naught x by 2 minus x square by 3r. This is the field inside. pi r dr is the area of the ring. J is the current per unit cross-sectional area. 2 pi r dr, look at the dimensions, it is area, not volume. J is the current per unit area, current density. This is the inside one. Outside is easy because outside the current is becomes constant. So that will be B into 2 pi x is equal to mu naught into total current. What's the total current? Put x is equal to R. So the total current will be when x is from total current. So if I substitute that, I get 2 pi j naught r square by 2 minus r cube by 3, that is r square by 6. Pi j naught r square by 3. That's your total current. So that would be mu naught j naught r square by 6x. Clear with this? So let me write down the final result here. So the magnetic field would be mu naught j naught x by 2 minus x square by 3r for x less than equal to r, and outside is mu naught j naught r square by 6x for x greater than equal to r. Yeah. Do look at the steps. Now you just need to plot the graph for this. Clear, everyone? Now, if you try to plot the graph, that thing on the top is definitely a parabola, which is a downward one. So if you plot B versus X graph, so X is 0, it is 0, the graph goes like this. It reaches the value here, and that is at R. How much is that? Mu naught J naught by R by 6, that is a value. And then it becomes like this. Once you're outside, it just behaves like a wire. Is the graph clear, everyone? That is a minus x square. It's a downward parabola. It's a this type of parabola. Itna kyo? Just think about this thing. Doesn't this look like equation of trajectory? Y is equal to x tan theta minus gx square by 2u square cos square theta. Isn't this the equation of trajectory? So this was actually part of that parabola. Clear with this? So the first part will be a parabola, and then it will be just a 1 by x curve. All clear with this? So I could give you any kind of thing here. This is how you integrate every time. First, you need to find the current up to x. So first you take an x radius disk, and in that take a small ring dr, and then find the current up to x. Outside is easy. Find the total current and you're done. Clear, no? Neil, Utsa, got this? Rehan, Arjun, Nishan,
So,
Kush. Clear. Next one. The magnetic field inside a cavity. Do you guys remember the field inside the cavity in electrostatics? When you have a solid sphere with a cavity, charge density rho, do you guys remember the field inside the cavity? Rho by 3 epsilon O dash, right, Ishan? Rho by 3 epsilon O dash, where O is the center of the big sphere and O dash is the center of the cavity. So this is O, this is O dash. If you look at this at the top view, this is how this looks. So here the cylindrical cavity, yeah? This is O dash and this is O. J is the current density, uniform. Find the field inside the cavity. In terms of O dash and J. Rho CP1, yeah, no, sure, that was also right. Let's finish it off. We'll be wrapping up this chapter today. We'll start EMI after this. If you remember how we did that, this was a question 37. This is what we did. Always remember, whenever you see a cavity, there's only one primary technique that we learned. Take the full sphere, subtract the small one, you'll get the cavity. And the first time you encountered this is not the first time. The first time you started that was in center of mass. When we started doing cavities, we did that exactly same thing. Find the center of mass of cavity, take full, take the small piece, you'll get this full. Then we did in moment of inertia. Then we did in electrostatics. Then we did in gravitation. Now we are doing in magnetism. You see a cavity. That is the main idea there. So we will take the full cylinder minus that small cylinder, and we will get this guy. This is O, this is O dash, O dash, this is O. Let this point be P inside, some random point. So this is P and this is P. And we derived the formula, the field inside the solid sphere was this, mu naught I x by 2 pi r square. So B inside would be mu naught I x by 2 pi r square. Adrit,
This solid sphere or cylinder?
what is this?
The cylinder.
So what is the problem?
So its formula would be different for a cylinder.
So we derived this formula for what exactly?
Okay. You said solid sphere.
Okay, fine, but you know, right? That was a doubt we have in the entire class. होता है, then this guy would be mu naught by 2 I by pi r square is j, that x is nothing but mod of op bar magnitude. Now remember, perpendicular to op bar, that is a catch. So the magnitude depends on op distance, but the field is this way. So I'm assuming the current is coming out of the plane. Okay, we are taking current out of the plane. You're getting it? So the field ka magnitude is this, but the direction is perpendicular to op bar. Similarly, when I do for this guy, so I'll just call this guy b1. Similarly, when I do for b2, this also will be mu naught, constant j, constant by 2, depends on the distance from o dash p, that is a magnitude, but perpendicular to o dash p bar. Meaning this field also would be something like this. That is your b2. So the field inside the cavity would be b1 minus b2. So field at point P would be b1 minus b2, which would be mu naught j by 2. The magnitude will become o dash bar, perpendicular to o dash bar. Clear? So it's like OP bar minus O dash P bar is nothing but O dash bar. OP bar minus O dash P bar can be written as OP bar plus PO dash bar. So this becomes OO dash bar. Just a vector there. So the field inside is constant. It's a good result. So B inside the cavity is mu naught J by 2. It depends on the magnitude OO dash, but the direction is not OO dash. It's perpendicular to OO dash. Keep that in mind. Have a look at this. This is the concept. Whenever you see a cavity, literally, this is the only way we can do. Because if you fill up the cavity, you'll get a symmetrical shape, and the cavity is also symmetrical shape. And how is the field ka direction? If you look at the field ka direction, it is perpendicular to OOP dash. So it'll be like this. It is uniform. Huh? That is how the B bar will look. I'll just remove these blue lines. So this is constant in magnitude and direction. So draw the line OO dash and drop a perpendicular for that. And the current is coming out of the plane. So right hand thumb rule, that will give you the direction. Have a look at this. So this total comes 3 times. Electrostatics, gravitation, magnetism. Field inside of the cavity. Cavity problems will come how many times? Center of mass, moment of inertia, gravitation, electrostatics. Gauss law may be cavity problems, but those are little weird. Those don't belong to this type of category. Clear with this? The next thing. Then infinite current sheet. This we already derived with the integration, but we will see how we can use Ampere's law to find. So if you have an infinite current sheet, let's say current is flowing like this. K is the current per unit length. So we know if you take the field due to this guy, it will be down. And we know if you take the field due to this guy, it will be up. So the net field will be horizontal. Similarly, here also the field will be this way. This though we proved it, even with that while integrating. Now consider an Ampere loop like this of length L. So here, this would be your DL, this would be your DL, this would be DL, and this would be your DL. And if you look at the magnetic field, here this would be B, here it would be B, here it would be B, and here it would be B. That means in the vertical wires, B dot dl will be 0. The field only will, B dot dl will be only in the horizontal wires. So integral B dot dl is equal to mu naught I. This will become 2 times B into L is equal to mu naught current is K into L. B is equal to mu naught K by 2. There. So this is how you can prove the field due to the infinite current sheet. This last time, if you remember, we did with integration and proved it. That was a more powerful one, but yeah, this was infinity. So here it is B into L. This is 0, perpendicular. This is again B into L, and this is 0. So totally you'll get 2BL. So if I call them, right, this is 1, this is 2, this is 3, and this is 4. B dot dl for 2 and 4 is 0. Because the magnetic field will be perpendicular to dl bar. So you just have to add for 1 and 3. Clear? There's nothing there, just a small derivation. Like, with an Ampere law, you can find the infinite current sheet more easily without integration. But if I give you finite sheet, again, story is gone. You can't use Ampere's law. This would be a HSA derivation. Huh? Find the field due to infinite current. I think no, this is not there. Solenoid is there. The result is more important for entrance purpose. Clear, everyone? Just a derivation there. There's nothing there. Next thing is infinite solenoid. We are just trying to find the results. Infinite solenoid also we derived using that finite one. But this thing gives you something more. Now, first thing, if you take two current loops, and if you try to draw the field lines, this we have to draw carefully. So if you look at in the middle, look at this thing. The field lines are going like this. These field lines are going like this. This thing now. Let it be. So this field is this way, and the red one ka field is this way. You can see the resultant is this way. Now there are infinite loops, right? So if you take multiple loops here, you will realize all these things create the field in the horizontal direction inside. Same way, if you take, remember, I'm taking only two of them. There are multiple of them. And when you go outside the field lines, I'm just exaggerating the figure. You can clearly see this is going this way, and this is going this way, and this field is coming downward. So outside the field will cancel out. Now, if you draw more of them, and if you try to overlap, you will see this. So the B inside will be along the axis. But once you go outside, you'll always find a component which will cancel out in the vertical direction. So the field lines will become almost vertical. Maybe you can take one more here. This field line will be like this. And if you take one more equidistant, one more will be like this. They will also cancel out. Like I said, because it is an infinite solenoid, every point is a midpoint, isn't it? You'll always find something symmetry on the right and left. They'll be always symmetrical. So end of the day, this discussion was to prove if you take an infinite solenoid, outside the field will be 0 and inside the field lines are horizontal. Now we don't know the magnitude. So what we do? We take an Ampere loop. We consider an Ampere loop like this. So outside B is 0. Here B is perpendicular to DL. Here is also B perpendicular to DL, and only in this part B and DL are parallel. And if you see here the number of turns, let this length be L. So integral B dot DL will be mu naught into I. So this will be only B into L, mu naught. What is I? So it's an infinite solenoid. N is the number of turns per unit length. So in a length L, how many turns will be there? N turns will be there. So there will be N into L into I. L will cancel. We get B is equal to mu naught Ni. This is the field inside a solenoid. Clear? So the diagrams, right? This is to prove that inside they will add up horizontally and the vertically they'll cancel it outside. And then take an Ampere loop and we will say there are N turns inside where N is nothing but N into small n into L. These are the number of turns that are crossing the loop. And each loop is carrying current I. Now, the main thing, the results are more important. This is for HSC derivation, it is there. You have to literally write all this story. Consider an Ampere loop. The field inside is horizontal and constant. The field outside, the field outside is 0. We have to write all that. Let me write down the result. Quite an important shape. Huh? We're going to encounter this again in EMI. This is what we call as an inductor later on. Infinite solenoid, that is nothing but the length of the solenoid is much, much greater than R. So B outside is 0. B inside will be mu naught Ni. Which is constant. Now, if you take a semi-infinite solenoid, we are going to use this today class only in EMI. So listen. So one side is infinity. The other side is a open end, which you can see. Now, if you look at the field lines, as they come to the center, the field lines will start going like this. Now they won't be uniform on the open end. Now the important thing is this. If you combine two semi-infinite solenoids, you should get mu naught Ni, isn't it? Now in that open end, if you look at the field lines, this is what you will notice. So that means if I add two semi-infinite solenoids, the field should be mu naught Ni. That means each one is contributing half of each, mu naught Ni by 2. And the best part is this. If you take the field like a horizontal component, that is also mu naught Ni by 2. So all the points on the open end, the horizontal component is mu naught Ni by 2. The magnetic field in the horizontal direction at open end is mu naught Ni by 2. Is that making sense, everyone? So basically, if you add two semi-infinite, so this and this together should give you field in the horizontal direction. Means each one is contributing mu naught Ni by 2 in the horizontal direction. Clear? The field is not same. On the entire open end, the field is different at different points, but all of them ka horizontal component is same.
But is the field uniform in before that also?
Before that also meaning?
Before that also you made Ni by 2. It's somewhere inside the solenoid.
You have to go really far inside only then, or else it is not. The field lines will start diverging somewhere before only, no?
Uh, but
We
here
can only talk
also,
about you can talk only about the open end.
there also the field will be mirrored Ni by 2.
The
Right?
horizontal component you're saying?
Here's the field inside. If you go a bit inside there, you have the same thing.
No guarantee. Why it should be mu not Ni by 2?
And that's what I'm asking.
It won't be.
Because as we go inside to infinity, it will tend towards mirrored Ni only, right? It should.
Yeah, right. What you're saying is right. If you go to infinity, at that point you'll get mu not Ni. It will tend to be not Ni. As you go inside, the field will not be mu not Ni. It will increase. It will not be mu not Ni by 2. It will increase towards mu not Ni.
It is not
Is that what
uniform
you're asking?
inside the
It's
circle.
not uniform. We can't say. Then we have to use a finite variable का formula है ना रे, वो use करके solve करना पड़ेगा, right?
Yes.
Hmm. Have same horizontal component of P. Now be careful. On the open end, every point has a different field, but all those things, the horizontal component is mu not Ni by 2. Where are we losing? I don't know what you mean by that.
So if we go towards infinity, then it tends to mu naught Ni.
Right.
So while we're coming to the open end,
That means, we drew like this, but some field lines will start originating from the middle, right?
yes, sir.
Basically, it's not like every line is coming from outside. Some lines will start somewhere generating here only. In case of infinity, that won't happen. Because for infinity, every point is a midpoint. So by symmetry, you can say all lines will come from infinity and go to infinity. But in a semi-infinite, some field lines are originating in the middle. Okay? It's not a symmetrical shape. That's what I'm saying. You can only discuss about the open end. Once you go little inside, what will happen? We have no idea. You can find on the actual end still using that finite cylinder ka, finite solenoid ka formula. And that last shape, we can do a small question on this. Let's say a question on this. So we have an infinite solenoid, a long one, radius r. This is a tightly wound, meaning there's no space between the wires. Someone took this and they made this into a solenoid of radius r by n. It is rewound. To radius r by n. Now, if I send the same current here, find the ratio of magnetic field before and after, find the ratio of magnetic moment before and after. Find the ratio of magnetic field and find the ratio of magnetic moment. Two different questions, everyone. Before and after rewinding. I hope you remember what is magnetic moment. NIA. Kaplan is the number of turns. Wait, we'll do one thing. Let's call this thing R by P, okay? Because they're already using small n for number of turns per unit length, you'll get confused. Let the radius become R by P. That P can be 3, 4, any number.
Will changing the radius affect the n?
I don't know. That is a question, right? I tell you the answer. What will you do? Call me from the exam. I'll come through the window and throw answers. Like, I don't know, God. I gave you 2 minutes for that only. You figure it out. Then I'll show you, no, anyway, where am I running away? Try. But not a bad question, though. 1 is to P and P is to 1. Nee, Lakshika, first one is wrong. It's a long solenoid. Huh? Long matlab infinity. That length was much greater than R. So even when you rewind, it is still an infinite solenoid. Others, do adjust your cams a bit. Make sure your faces are visible on the screen. Maulika, Vartika, Vedin, Aryan, Ali. Where is this Ovian? He left. Who else is missing today? N by P for magnetic field. First thing, let's see what Adrit said. If you make the rewinding, will the number of turns change? Now, what will remain same? When you open this, the length will remain same. So what is the length of the wire here? Total number of turns, let's say N into L. Meaning I can argue in different ways. This is one way to argue. Let this total length be L. Number of turns be N. So length of the wire will be how much? Or actually I can simply say you understood that. So if I make this thing N by P, I'll get more turns. So this guy will become, since the radius has decreased, this was R and this was R by P. Number of turns will become P into N, and obviously length also will become P into L. Make sense? Basically, number of turns into circumference must be constant, isn't it? The length of the wire is number of turns into circumference. That is one way to argue. But think of like this, right? When you say thickness of the wire, you are keeping the wire touching like this. So like this, if I keep wires, you tell me, what does it depend on? Doesn't the number of turns per unit length depend only on the thickness of the wire? Is that making sense? The number of turns per unit length will depend only on the thickness of the wire. For example, listen to this thing. So let's say if this was your wire, this is one turn, okay? And let this thing be D. This is the diameter of the wire. So as long as the diameter is same, it doesn't matter how many turns you make, the number of turns per unit length will remain same. So you can say number of turns per unit length is simply you have one turn in a diameter D. Does that make sense? The D is the diameter of the wire. Now, if you make the wire smaller, does the diameter change? Now, when you made it into smaller turns, you made it like this. But the diameter is still the same, isn't it? So number of turns will not change when you do rewinding. Number of turns per unit length won't change per rewinding. So be careful with that. So number of turns per unit length. Let's have the capital N actually. Getting confused unnecessarily. N is the number of turns. Small n, P, too many symbols. This is N by L. Here, what is small n? Pn by Pl. So that is still N by L only. So you're done. So first one, the magnetic field is equal to mu naught, constant N, constant I, constant. It does not change. 1:1. The second one, magnetic moment. Magnetic moment is the total number of turns. This is number of turns into current into area. So this is B proportional to number of turns into R square. So mu1 by mu2, number of turns will be N R square by number of turns are Pn, and this is R square by P square. P is to 1. Right, Ishan, you got it. Others clear with this, the magnetic field won't change. The magnetic field is independent of the radius for infinite solenoids. And this is the main idea there. The number of turns per unit length will depend on the thickness of the wire. If I use thin wire, I can put more turns in that same length. If I use a thick wire, I'll put less turns in the same length. It doesn't matter whether you make the radius big or small, the thickness will not going to change because of your, making the radius. This is the diameter of the wire. Clear, no, everyone? Adrit, got this? It's a good one. Remember this thing. We're going to do this again in EMI. There I'll ask you find the ratio of self-inductance. So this thing you can ask, rewinding thing you can ask in magnetic field, I can ask in this. We will see this again, same question in EMI. Clear? The last shape is the toroid. We just have a formula for this. This shape is one of the most studied one right now in the world. This is the shape which we are using for a nuclear fusion, a toroid. I hope you know what is a nuclear fusion. You take lighter nuclei like hydrogen or helium and you try to combine them into a heavier nuclei. In this process, you get energy. The best part about this thing is, unlike a nuclear fission reactor, where we use uranium and break it, uranium produces a lot of radioactivity. The materials are highly radioactive and you need to store, and there's a lot of problem. But in a nuclear fusion reactor, the best part, you get the waste product as helium. So there's no toxicity, nothing, you're safe. But then I keep saying, if you're getting something for good, there's always a catch. The headache is nuclear fusion reactor. Starting it is the biggest headache. Cyclotron is not there for the mains portion. So advanced, let's see, we'll see that later on. But I think we can do that also. They did remove it. So this is A, this is B. So here N is the total number of turns. So we will not do the proof. We'll just take a small ampere loop here at a distance r. And then we do integral p dot el is equal to mu naught I. This will be b into 2 pi r into, so this loop will cross n turns. So it is mu naught into ni. This thing actually looks like a solenoid, which is folded into a circle. Mu naught ni by 2 pi small r. There. This is the field between B to A. Field outside is 0. That's the toroid. We have only this much. There's only field between A to B. B is 0 for r less than A and r greater than B. Check it out. So the biggest problem with the fusion reactor is you need very high temperature. When we say high temperature, we're talking about 10 lakh degrees, a million Kelvin. Now the problem, creating the temperature is not a problem. We have the kind of, we can create such temperatures. The problem is after creating, where will you keep this? There is no container which can sustain the temperatures. Container will get destroyed. So you need to keep this thing floating in space. So in order to keep them floating at those temperatures, right, there is electrons are completely removed from the nucleus. What you have is a plasma, charged particles. So we use a combination of magnetic fields in order to keep it floating. I think I have that thing. Let me show you how it looks. Yep, I don't have it. This is a cycloid, cyclotron. Okay. So it is that. You can search it out. It's something called ITER, International. I forgot what is the name for that. E is that experimental reactor. International tokamak, I guess. I don't remember this thing. Check it out. It's called ITER. They're building one in France. They'll complete it by 2035. So we do have a reactor right now in Korea. It's called a tokamak. Nuclear fusion, they did sustain it. They created temperatures of 1 lakh Kelvin. They were able to get energy also. It is like 1:1 ratio. They're sending energy 1 unit, they're getting 1 unit. So experimentally, it is working. But to create a commercial reactor, you need 1:300 ratio. For every 1 unit, you need to create 300 units of energy. And if you have seen Spider-Man movie, right, in that the villain actually creates nuclear fusion. Remember that Spider-Man 2 movie? That guy, Octopus guy or something, I don't know what you call them, the Dr. Octavia something, he has his hands, he creates a sun. You guys remember that? There is a movie there, you can check it out, Spider-Man, they create a sun actually. So that's actually a nuclear fusion. That is also a method which people are trying, but that is not sustainable. It's very difficult. Tokamak, the toroid one, is the most commonly accepted one right now. You can search about it, nuclear fusion. But for us, though, we have only this much. And yeah, with that, we are done. Now, this cyclotron is actually removed from the portion, but I think we can discuss a bit. We'll finish it off that also. Because they can ask an advancement paragraph, they can ask. So cyclotron, right? Primarily, we use it in a particle accelerator. It is useful to accelerate charged particles to high velocities and bombard them. That's what we do in a Large Hadron Collider, LHC. Ever remember this experiment that Rutherford took the alpha particles and bombarded to the gold foil? So do you think the alpha particles automatically went and collided? He must have called, oh, alpha particles, use the power of the god and go and collide with the gold foil. So it doesn't work that way, right? You don't use magic. You have to somehow direct those alpha particles and bombard them. So this thing, right, is used to accelerate atomic particles. To very high speeds. We are talking in the range of speed of light, 0.9 g and something like this. This was the LHC. You can see that circular thing. That is your Large Hadron Collider. This is there in CERN, Geneva. This was built somewhere in 2001 or 1999 something. I was in school that time. I remember this very well. It was a big deal in the news. I think I was in 5th or 7th. I don't remember. But they took an interview of the scientist and they were about to start this. So the scientist in the interview, right, he told there is a possibility of getting a microscopic black holes during this collisions of, they are going to actually accelerate alpha particles and bombard them. So one will come from the top and the bottom types and the collide. So when you collide protons and alpha particles into each other, they break down into finer particles. We get all these muons, bosons, and all that stuff. We'll not get into that. So he said, there is a chance of getting a subatomic particles. That is what the scientist said. And he said, these things are so small, they won't affect anything, they will vaporize. And they're gone. Now, if you write like this, no one will read your newspaper, right? So this guy, what he wrote in the newspaper, the scientist says there will be black holes, there's a chance of Earth getting destroyed. Because it's a black hole, right? This was in the news, and people started making noise like, end of the Earth, ho gaya, we are bringing the devils from the other universe, dimension, all bullshit. As usual. Now, why do I remember this so well? Because next day in the class, we started shouting in the class, we want holiday, we want holiday. The teacher came and said, why you guys need a holiday? Ma'am, tomorrow Earth is going to get destroyed, so we need holiday tomorrow. मतलब you see ना स्कूल का माइंडसेट वही है, अर्थ को कुछ भी होने दो, मतलब let the earth get destroyed, हमको हॉलीडे चाहिए, मतलब बस. Teacher didn't understand whether to laugh or cry, but we didn't get a holiday and the earth was safe. So, yeah, it didn't work out. We would have got a holiday, but. So the idea was, so they start somewhat like this. This thing has a 27 kilometers ka circumference. Pretty large. This thing, what you're seeing is the top view. You can say that is one of the most advanced thing, a facility built by humans. This is how it looks inside. The people have small vehicles inside, taking them everywhere. Now let's see how this whole setup works actually. The concept is pretty nice and simple. We take two parallel plates. We connect this to alternating voltage. We'll see why is that. So this is what we do. So first, let's say this is positive and this is negative. So we leave a charge particle here, let's say plus Q. So between the plates, there will be a field. Because of the field, this particle will accelerate, increase the speed, and it comes out. Once it comes out, we will have a magnetic field outside. Inside, there's no magnetic field, but outside, the electric field is zero because the field will come only due to the plates. This d is the distance between the plates, and these plates are called d's. So once it comes out, because of the magnetic field, you'll start going in a circle. And then again, you will enter inside. Now look at the problem here. If you leave the direction of the field in the same way, now what will happen? If this was still plus and minus, this particle will decelerate, 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 and stop. So there is no use. So we flip the field. We suddenly make this field. We will make this plus and make this minus. Now again, it will go faster. And this time again, it will come out. This time will come out with a much higher speed, it will go a bigger circle. Again, it goes inside. Again, we flip the field. Again, it goes in a bigger circle. So every time it goes between the plates, the speed will keep on increasing. And every time it comes out, it will come out with a higher speed. It will go in a bigger and bigger circle. So the catch is this. So that is how you can keep on increasing the speed. The charged particles are accelerated by the electric field between the plates. Magnetic forces anyway don't do any work. We call them Ds. Now when it comes out, the magnetic field will turn it. Due to magnetic field, it goes in a circle and enters the plates again. And we reverse the polarity of the battery. Right? At this instant, we reverse the polarity. So the particle will again accelerate. If you leave the same polarity, it will slow down. And particle speeds up again. And we keep doing this. Now, the best thing about this, how can you control this? I'll show you a better diagram. There. This is the diagram. This is the top view. This is the side view. So you start from here, this thing goes in a circle, goes in a circle, goes in a circle, goes in a circle, finally comes out. This is your side view. That is a side view there, and this is another view. Able to see this? Now, the best part about this thing is, we know the frequency. We know the time period is 2 pi m by qb. Did you observe one thing? This is independent of the speed. Therefore, the frequency will be 1 by t. So this will be the frequency of the source, which is constant. That means this particle is going to enter the plates after a constant time interval. Every t by 2, it is going to enter. The reason why this works so nicely is because the frequency is constant. You can keep a constant frequency source. So let me write that in the next page. So in this thing, right, the main questions are these only. What is the frequency of the source? The time period is 2 pi m by qb frequency of the particle. Remember, first time it enters, the polarity will go from plus to minus. Again, it will enter, it will go from minus to plus. So that is one full oscillation. In this case, second case, yeah. That is how you have to create a magnetic field outside, right? So you can use electromagnets also, but that way you can control the level of the magnetic field, which is 1 by t or qb by 2 pi m. This is also the frequency of the source. This is the one question they would have asked, but mains में अभी नहीं है. That is one. I think it is there in HSA. I don't remember.
So it will be twice or equal.
Equal. Then we also know radius is equal to mv by qb. So the velocity will be qb by m into r. That means your final speed will depend on the last radius, this radius. So the higher the speed you want, the bigger you have to make. And that's the problem we are facing now. This LHC, right, already reached, it's like, it does make the particles pretty fast. They're trying to construct one more. LHC is 27, they're trying to make one with 100 kilometer circumference. Expensive experiments, where here R is the radius of the beam when it comes out. This is the second question. Find the speed when it comes out. Now in this, there are few precautions also. Electrons cannot be accelerated effectively in a cyclotron. You can accelerate, but not effectively. This they asked once, I think in CET or somewhere. Which of the following particles cannot be accelerated in a cyclotron? Electrons. Reason, since mass of the electrons is very small, they reach very high speeds. And the relativistic effects come into the picture. What is the relativistic effects? The mass of the electron will be m naught by root over. We'll not get into this, but it does change. M is the rest mass. So it does depend on the speed of the particle. Now, since the mass is changing, and we know frequency is proportional to that q by m, f starts changing. Which we can't do. It's very difficult to adjust every time. So the electrons will actually get pushed out and they'll start hitting the walls. This will happen even with the other particles also, but for electrons, it will happen much faster. So like I said, we are doing a very simplistic case. You have to take everything into picture. So this LHC is not that easy like we think. And forget about that. You are taking two alpha particles ka beam and you're making them collide into each other. Just imagine how difficult is that. And after colliding, after collision, they'll break into small particles. How are you detecting them? So I think that when they constructed it was $6.5 billion. This was 25 years back. But that is pure science research, actually. If you see that, that is a pure science action. That's about a cyclotron. So that's it. These are the main things. Just have an idea about the concept, because advanced, if at all they ask you, they'll give this as a paragraph and they'll ask you. HSC, it is there. They'll ask you to draw the cyclotron diagram, this thing, and they'll ask you to prove something. So you know how to write the story now. Clear with this? Clear, na? Adrit, you got it now? Why the frequency is F? Because see, from here to here, this becomes plus, minus, again from here to here, plus, minus. So this is one full oscillation. So this will take t by 2, t by 2. So in one time period, you have to come back again to the same position, isn't it? So it is repeating after every one time. So frequency is 1 by t only. It is not half of it. Be careful with that.
And we take the distance to be small between the plane.
It has to be small,
What is the time
or else field won't be uniform.
And time will be affected also with the distance.
We can neglect it. It is too small. Clear, everyone? So go through this. We have done almost 47 questions in the notes. After this, we do have bar magnets and magnetic materials. That is proper mains only that we will see in the end. Again, in that there are some 10, 12 formulas, ratta marne. So we will keep all that inorganic physics in the end. The next one is EMI, electromagnetic induction. Quite an important chapter. You can think of it like, in mechanics, how was rotation? EMI is like that in entire electromagnetism. Pretty good weightage. You can say EMI and AC, these two chunk has a pretty nice weightage. Advanced के लिए बहुत important है. So let's see. First thing, the magnetic flux. The symbol is phi. This is similar to the Gauss-Locker flux. So flux is proportional to number of lines passing through an area. It was the same definition we wrote in the electrostatics also. But in this case, it is the magnetic field lines. If electric field lines are passing, we call it electric flux. If magnetic field lines pass, we call it magnetic flux. So if you see, all of them have same flux. As long as the number of lines are same, I don't care how big is the area, I don't care about the direction. The number of lines must be same. But the flux cut definition is integral B dot dA. Now this we did study, in Gauss law. The idea was the same. Remember, here suddenly depends on area and angle. Why? If you study in terms of field lines, it doesn't depend on area, because B bar is nothing but number of lines per unit area. So area terms will cancel. You get number of lines. I hope you remember. So this you can refer. I think it is the second page, I guess. First page, Gauss law. Yeah, this is Gauss law of page 1 and page 2. Exactly same thing mathematically. There is no difference. Integral B dot dA if B bar is constant. Then the flux would be B bar dot A bar. This is your area vector. This is your B bar and this is your theta. So you can write this as mod B, mod A, cos theta. So theta is the angle between the area vector and this thing. Clear? Same definition. So you can study in terms of lines, and that time area angle won't matter. But if you study in terms of B bar, area and angle will matter. Next one. Turning the page. Gauss law for magnetic flux. So do we have anything like Gauss law here? because mathematically they look the same. So mathematically you should have something similar for this also. Luckily, integral, if you take b dot dA, once I put that circle inside, I'm talking about a closed surface, is 0. The magnetic flux is always 0 for a closed surface. This is integration over a closed surface. Why? Reason. First thing, magnetic fields are always closed loops. So if you take some closed surface, for every line that enters, there will be one line which will leave, isn't it? The flux will be always 0. That is the most easiest way to explain why the flux is always 0. Because there's a closed loop. Number of lines entering is equal to number of lines leaving. Or if you want to study in terms of charge, we know electric flux is nothing but charge enclosed by epsilon. But here in place of charge, we have North Pole and South Pole. So magnetic monopoles don't exist. You can't have a single North Pole or a single South Pole. They always come in pairs. That means the total charge inside, we call it magnetic charge or pole strength. We will talk about that in bar magnetism. Magnetic monopoles don't exist. So you can argue like that also. Since North and South Pole will always come together, it's like the total charge is 0. Therefore, we can say pole strength. This is synonymous to magnetic charge. So North Pole is like plus Q and South Pole is like minus Q, just for a reference. Because mathematically there's no difference. We call this pole strength. So you can argue like that also. The total charge is always 0 in a closed loop. Or you can always say the number of lines entering is equal to number of lines leaving. So the flux is 0. So there is no Gauss law for magnetic field. You are saved. That's so straightforward. We know the flux is integral b dot dA, what we did. Let's do a few questions on flux and then we'll go ahead. All clear with this? Okay, right. Let's see a question. We have a magnetic field region. Let this be root 3a. We have a loop here. Equilateral triangle side A. This is going with speed u. Let this distance be some a. So initially it is somewhere here. T0, this is the scenario. So an equilateral triangle enters a magnetic region with constant speed u and leaves it. Plot the flux passing through the triangle versus time. Let's get this. This is more of a geometry again. Then nothing flux is being to it. Plot the flux versus time. Anyone got the graph? Udyan, got the answer? Focus everyone. Palaksh, any answers? There's nothing there. This has nothing to do with EMI. Just test your skills of how to draw diagrams and calculating areas. There are two parts in the problem when you're entering. So when you are entering like this, let this be some distance x. This is 30, this is 30. So I'll just take it as theta. So this length will be 2x tan theta. I could have taken any triangle. So area would be half base into height. So half into x into 2x tan theta. So whatever is that, area is proportional to x square. That much for time, and we know x is equal to ut. X is proportional to time. Now the same thing when it is leaving, it's like this. So again, same idea. If I say this is x, just I'm giving something, but this time I'm interested in this area. So this area would be some constant. There's a total area of the triangle minus some kx square, isn't it? Right? X square tan theta, whatever it is. Now remember, this is some constant. So that means while you're entering, the area is proportional to x square. While leaving, the area is proportional to constant minus x square. So if you try to plot this graph, flux versus time, now you can see clearly for some time you won't enter inside. So flux is 0. So flux will be 0 for some time. You can calculate that A by U. And then it is proportional to x square. So this would be a parabola. And once it has entered inside completely, now if you see this is root 3a, this is only root 3 by 2. Means for some time you will be inside completely. So flux will become constant. And this is minus x square. This is an inverted parabola, something like this. So this graph must come down like this. There, that is how it is. So this is completely inside this region. I'll just mark in green. This is completely inside. That is the reason flux became constant. This region, you're coming out. This are entering. So there are three parts in the problem: entering, completely inside, and coming out. So there'll be two parabolas. One is an upward parabola and one is a downward parabola. Agreed, everyone? Isn't this how this parabola will look? C minus kx square. This is minus x square. C minus x square will look something like this. It's a decreasing flux. It's a downward part of the parabola. That much we know. Since the flux is decreasing, it's a downward part of the parabola. Because see, the problem is this, there'll be an option like this. Most people will mark that because it looks nice and cute and symmetrical. And they will think this only flux is decreasing, but the headache is this. Clear? There. Take a break. Come back by 7:7. We'll continue from here. सर एक लाइट मंगा ले वो स्पीकर होगा सर बराबर डायमेंटर में दिसते एवरी 20 मिनट इट्स फ्लिकरिंग राउंडिंग नहीं गेम Yep, comes on everyone. Next one. We have an infinite current carrying wire. We have a loop, square loop. Side A. This distance is d. Find the flux in the loop. So basically, this infinite wire is creating a magnetic field, and that magnet is creating flux in this thing. Find the flux in the loop due to the magnetic field of infinite wire. Let's get this. This was an easy one. Let me add one more question. Same thing, infinite wire I, but this time you have a circular loop. Of radius r. The loop is touching the ring is touching that infinite wire. Find the flux in this also. First was easy. You got the first one, go for the second one. First one, how to do? At a distance x, take a small rectangle of thickness dx. So the flux will be magnetic field into area. Both are perpendicular anyway, area vector and this. So B bar would be mu naught I by 2 pi x. That is the field due to infinite wire. So flux will be integral mu naught I by 2 pi x into a dx. Limits will go from d to a plus d. This was easy. Mu naught I by 2 pi a ln a plus d by d. I hope that was clear, everyone. Check it out. Can you do for the circle? Try, I'll give 2 minutes. Idea is the same. Anyone not clear with the 2a part, please ask me. Any doubts on 2a? Try the circle. You got 2 minutes. There, I'm not teaching anything big deal, only calculating flux. One step at a time. You know how to calculate flux? Things will fall in place. Any ideas how to choose an element? Answer comes pretty nice. What will I do with that? Hi, Shan. What will I do with that? Solve karo na then. Give me the final answer, na. Just imagine asking your mom, I'm hungry, give me something to eat. Your mom comes, right, gives you 2 carrots, 2 brinjals, 2 potatoes and say eat. How do you feel? And she'll ask you, ये सब क्या है? He said, हाँ मैं अभी भाजी बना रहा हूँ. It is like that. Solve. Give me the final answer. Why do I care how it is? It's more of a max problem than physics. It's about choosing the elements properly. Now, first thing when you see a circle, well, the first thing I like to do is take everything in terms of thetas. But let's see how to do this. So from the center, that is a symmetrical thing there. At a distance x, take a thin arc. Idea to why you have to take end of that element like this only. This was radius r. This is y. This is x. This thickness is dx. And let this angle be theta. So that area of that strip. So this distance will be how much? This distance will be r minus x. So the flux will be, the small flux will be magnetic field mu naught I by 2 pi r minus x. Because mu naught I by 2 pi d is the distance from the wire, into that area of that strip will be 2 times y into dx. Is this clear, everyone? That is a magnetic field and that is a thing. Now everything in terms of r and x. So from here we can see cos theta is equal to x by r. So dx would be minus r sine theta d theta. So I want to eliminate everything in terms of x and y and bring everything in terms of theta. Right, and I also know it's a circle, so x square plus y square is equal to r square. Or I can write y is equal to r sine theta. That also would work. Let's dump everything here. So I don't want to get in terms of x. I want to replace everything there. So r minus x. So this will be r into 1 minus cos theta. This is 2. Y is nothing but r sine theta. And dx is nothing but minus r sine theta d theta. Hmm. Two will cancel. 1 r will cancel. You know, I by 2 will cancel. Pi 1 r is also gone. So you know, I r by pi. That would be sine square theta d theta by 1 minus cos theta. Actually, no, sine square theta ko I can write it as 1 minus cos square theta by 1 minus cos theta d theta. With a minus sign. That is like a plus b, a minus b, na? Minus mu naught I r by pi 1 plus cos theta d theta. I hope I didn't goof up. Looks fine. Then integrate this. Minus mu naught I r by pi. Limits will go from, I took theta from here. So this point mein theta would be 0, theta would be pi. Because when I go from 0 to pi, all the elements will be covered. Limits will go 0 to pi, 1 plus cos theta d theta. Cos theta integration will be 0. There is only 1 left. I ended up with a minus sign, but okay, I needed a magnitude anyway. Minus mu naught I r by pi into pi. So just take the magnitude. Mu naught I r. The reason you're getting minus sign is because you have taken this rotation. Something like that. So it's just a magnitude. Answer is pretty good, easy to remember. Mu naught I r. The main idea here is the x and y looks pretty messed up. If you can convert all of x and y into one variable, I think theta would be the best variable. Or you could have done that y is equal to root over r square minus x square. Actually, ये भी होता था r minus x into dx. This is also fine integration. मतलब that would be root over r minus x by r plus x into dx. Then you'll do integration to substitution. That also works. You guys are experts in integration, so I won't say. Clear with this?
Sir, I did the second method that you suggested, but I'm getting
Mhm.
a ln sine 0 there.
Yeah, you moved up somewhere. Check it out. Just a matter of integration. I think if you have written till here, I think you got the job done. Physics got over here. Clear? Next one. Any doubts on this thing? It's more of a calculus question than physics. Physics got over after writing B into area. Turn in the page. Any doubts? Clear, na Arjun? Aditya? Adrit, clear?
Yes, sir.
Great. We have a semi-infinite solenoid. Infinity. Now, when you look at the field lines here, so this field lines from the outside, right? This is the last field line which is entering, the green one. These are the green ones are the last field lines to enter the open end. So a lot of these field lines are entering, getting it? And the green ones are the last field lines which enter from the open end. So this radius is capital R. So these green lines at us after far distance, after infinity, they'll be at a distance x. So basically, xn is the distance of the green lines from the axis at infinity. So if these lines go to infinity, very far off, the distance becomes x. This is what I was saying, there will be some field lines which originate in the middle also. So there are lines coming in the middle because it's a semi-infinite, it is not symmetrical. So the question is find x. Again, I'll explain the question. You took a semi-infinite solenoid. So field lines from outside are going through this and going to infinity. So when these lines are entering, if you see there are infinite lines going in, getting it? I just drawed a few of them. So out of all of that, this last green lines, those are the last lines which will enter. They'll be almost 90 degrees and they'll enter inside. After this, there is no line which will enter inside from here, gone. So the question is, these green lines, when they go to infinity, they'll be at a certain distance x from the axis. At infinity, lines will come parallel, right? So what is the distance of the field line from the axis? It's a good one. Think, take a minute. We have one answer. We have two answers, right? Isha and Lakshika, both of you got it. Anyone else? See, I will just take this like a cylinder. So this line which enters here, it becomes like this. Now, if you consider an area, the lines are entering here. Now, do you remember? I told you for all these lines, the horizontal component Bx is the same, isn't it? No matter which point you take, all these things have the same horizontal component. So the flux entering will be magnetic field mu naught Ni by 2, the horizontal component into area. And after a long time, if you take a disk here at infinity, this field becomes mu naught Ni. Now the flux entering must be equal to the flux passing through that. So flux at infinity must be mu naught Ni, and you're saying this radius is x, is pi x square. The flux must be equal. Why? Since the number of lines are same, isn't it? Every line that enters here must be between these green lines, isn't it? All the lines entering between the green lines must be within that x square region. After this, some new lines are coming from here. I don't care about them. Since the number of lines are same, the flux must be same. Every line that comes between the green must pass through this disk. Therefore, I can equate the fluxes. So mu naught Ni r square by 2 is mu naught Ni pi x square. X is equal to r by root 2. It's a pretty good question. That's the reason I told you that semi-infinite solenoid thing, you should remember the result, that the horizontal component is Bx. I don't know the field of each one of them, but I know the horizontal component is Bx. And for flux to anyway, area is this way, so you should take the B also in the direction of area. The perpendicular components are anyway useless. They don't create flux. So the flux entering the open end must be equal to the flux within that green region. Make sense? Easy question, but you should know this concept that the field will be mu naught Ni by 2 in the horizontal direction. Clear? Next thing. So there, that is one thing about calculation of flux. Then Faraday's law of electromagnetic induction. If you talk about Faraday, right, this guy, if you see, it is a pretty cool story about him. He's like a typical movies mein dekha hai na, hero is very poor and all, and he rises from the ashes to something of that sort. This guy is seriously something like that. Faraday was actually a bookbinder. We are talking about late 1800s. Books are quite precious, and people used to send the books for binding. So Faraday was actually a bookbinder. He didn't have any formal education. So this guy used to read all the books that used to come for binding, and he used to learn stuff from that. So during that time, right, the Royal Society of London, the head was, Humphrey Davy. So this guy was the head of the Royal Society of London, and during that time, right, it was the age of science. People were discovering a lot of stuff, right? And one second. Yeah. So people were discussing a lot of stuff. If you see that during that time, 1800s and all, there's nothing called physics and chemistry. Everything was science. There is no subject called chemistry till 1910s. So that is the reason if you look at the scientists' names, that same guy was working in chemistry, that same guy was working in physics. So at that time, current and magnetism were like a trend. So every weekends, right, there used to be lectures. People used to gather because that time we didn't have any Netflix and all, so people were bored. So they used to come to watch the science shows. So these people literally used to have, lectures in big halls. They used to demonstrate the whatever science they discovered or experiments in the, week. So Faraday used to attend all those lectures. He used to sit there and write notes. This guy did that for almost 2 to 3 years. I'm telling you all this from a documentary called E is equal to MC square. Very beautiful documentary. 1 hour 40 minutes if you have patience. But I would say keep that in your checklist. You can watch it after the advanced exam gets over. That is it. Like I told you, right? One of his senior used to do that. Any movie he wants to watch, he used to make a checklist. I think that guy had a list of more than 110 movies. After the advanced exam got over, he took a 20 days break and watched everything. वो होता है commitment. Movie भी देखना है, exam भी लिखना है. So both the sides commitment. Anyways, it's a good documentary. So in that he explains everything like this, what I was saying. So he writes the notes beautifully, everything. After 2-3 years of writing all that notes, he compiles them into a nice book and he gives it as a gift to Humphrey Davy. So this Humphrey Davy guy looks at the book and he gets really impressed. Yaar, what a book, yaar. Matlab, because this Faraday, right, also writes his own insights. I think in this experiment, it could have been like this, that, this, and all. He gets pretty impressed and he calls him inside, call him in. So Humphrey Davy expects he is must be a PhD student or must be a big scholar. And when he looks at him, he feels like, yeah, this guy is looking like a beggar. So appearances do matter. And Humphrey Davy really feels like, what the hell? And he says, okay, thank you for the book. You can go now. So he is not entertained at all. And while going, right, Faraday says, sir, I'm ready to work for free also. If there is anything, please let me know. He says, okay. So after a few weeks, right, Humphrey Davy is doing some experiment and sodium hydroxide falls in his eye. He becomes blind in one eye. He needed help. Then he thinks about this guy. Like he said, he'll do work for free. He calls him. Who doesn't want free worker? So Faraday comes there. He works as a lab assistant. So his job is to clean the chemicals, keep everything in order and everything. He works there for a few years. And one day, right, these people are doing an experiment. Some scientists and all, they're sitting there and doing an experiment. So magnetism was a craze that time. So they took a current wire and they kept a compass here and the needle was deflecting perpendicularly. Now though we know the force is IL cross B, the force is perpendicular to the current. The scientists were like, these people are thinking, yeah, if the electrons are going like this, the charged particles are going like this. Because of this electron, there should be electric force in this direction. Then therefore the needle should be this way. But for some reason, the needle is perpendicular. So these people are thinking, see, it is a completely new thing. Now, for us, it is obvious. It is not obvious for them. So they were brainstorming and all these lab assistants are standing beside, and Faraday gives them a say. They say, like, sir, maybe this is not the electric force. Maybe this is a new kind of force which will act perpendicularly. They say, Faraday, you can shut your mouth. You're a lab assistant, be like one. Don't try to be over smart. So this guy feels really bad. He goes back. He and one more lab assistant, right, in the night, he's really pissed off. He designs an experiment. This you need to understand. Being a scientist doesn't mean you'll sit there and write theories. Being a scientist meaning you need to design an experiment, right, which can actually prove your thesis. And that is the most difficult part. You're getting it? It's very important. The ingenuity of a scientist depends on the kind of experiment you can do and prove it. For example, if you remember in this we did, remember the Thomson experiment. Now, the best thing about this Thomson experiment is, look at this. You just used simple projectile and everything and you proved QIM. So that is the thing, the ingenuity about the experiment, right? So being a scientist is that. How do you design an experiment to prove what you're saying? So Faraday did something. So this guy designed an experiment. He took a container. He took a magnet. He filled this with mercury. He kept a rod here. He took a Leclan cell, the chemical cell. So he connected one wire to the rod and one wire to this thing, and this is mercury. Why mercury? Mercury is conducting. So the moment the switch is closed, current is passing through the wire, through the rod, through the mercury, and the circuit is completed. Now see what happened. Now we have a current carrying rod. The magnetic field is there. This rod started rotating in a circle. Now you tell me, if something is going in a circle with uniform speed, force is in which direction? Perpendicular. He said this can't be an electric force. This was a simple thing. This was a proof that this thing is generating a magnetic force which is perpendicular to the current flow. Kidding it? Faraday proved it. But what Faraday didn't realize, he did more than that. He invented the world's first electric motor. Isn't it? This is the world's first electric motor. One. Second thing, he proved chemical energy becomes electric energy becomes mechanical energy becomes heat. He proves that energy can form from one form to another. Third, he proved there's something called a magnetic force in perpendicular. He did three things in one experiment. Maybe he didn't realize then. He publishes a research paper on this. Right? Humphrey Davy comes barging into his room and is pissed off. Like, how dare you are a lab assistant, you are publishing papers. Faraday says, boss, I did everything on my own. I didn't take it from anyone. And it is my friend's encouragement. So you have no right to tell what I can do. Humphrey Davy gets really pissed off. He goes to the publication there and he tells them, this Faraday copied everything from a German scientist. So he's a plagiarism and all. That's what happens when you're growing. People do get pissed off. Then Faraday goes to the German scientist and he tells him, boss, this is what I did. Are you doing something like this? German scientist says, I have not done anything like this. So therefore, it is proved Faraday did everything on his own. He gets this patent. He becomes pretty famous. And then after that, few years down the line, Faraday becomes the head of the Royal Society of London. The Humphrey Davy guy gets so pissed off every time anyone asks him about Faraday. He says, like, I'm greater than Faraday. Why? Because I found Faraday. That's his famous statement. Since I found Faraday, so I'm greater than Faraday. He gets pissed off. And then story goes on like that. And Humphrey Davy actually dies because of nitrous monoxide poisoning. Because this guy has a habit. Before going to that every show, right, he used to breathe in that nitrous oxide, which is a laughing gas. It relaxes your muscles and makes you comfortable. So he used to give shows like that. I think maybe there's an overdosage or something. He dies because of that, but that's a different story. Story goes like that. So that is how a bookbinder becomes the head of a Royal Society of London. It's a pretty nice documentary. You should definitely watch. It is worth watching. He died laughing. Aryan says Humphrey Davy died laughing because of nitrous oxide. That was a good one. But let's see. That we don't know how he died exactly. He died that they say that is one of the reasons. So it's a good one. Next thing. So let's see. What was this? So Faraday, right? During his time, he worked on a lot of stuff, and this was one, induction. Now, like I said, Faraday is a completely experimental person. So he founded all this from experiments. So he says, so this is what we did in the experiment. The first thing, we took a loop. We have a ammeter. So we have a coil here, and you kept a magnet. North, south, magnet is at rest. The field lines are going. Nothing. There's no current. Fair enough. Then he took that same coil, but this time he moved the magnet. Now, when the magnet is moving this way, he observed there is a deflection. Current started flowing in the wire. Same thing. This time, when you move the magnet backward, again there is a deflection, but this time the current flowed in the opposite direction. Now, Faraday didn't know why this was happening. So one thing is clear. Whenever the magnet moves, there is a deflection here. This is an observation. He said, fine. One thing is clear. This is depending on the magnetic field, but only magnetic field is that nothing is happening. It is depending on the changing magnetic field. So fair enough. This was the first part of the experiment. The second part of the experiment, same thing. We take this coil. Again, I'm telling you in a very simplified form. They must have done it in more varieties and all. You keep the magnet. Magnet should be there. So that is clear. If there's no magnetic field, nothing happens. and then increase the area of the coil. Even then we see a deflection. Direction and all we'll see later on. But it is clear, if area changes, there is a deflection. That's great. Then we have the coil. Keep the magnet at rest. This time rotate the coil. Even then there's a deflection. So one thing is clear. This thing is changing whenever the B is changing, whenever area is changing, whenever theta is changing. So then he says that means first thing is clear. Because there is a current, there must be an EMF. That is the first conclusion. It is all reverse. You see the current first. How can you get a current in a resistive wire with some resistance? There must be an EMF. So this implies EMF must be there. Now, if you ask Faraday, how do you know? I don't know. It's an experiment, and that is the only way I can conclude. And he says, so this EMF, whatever is there, is depending on B, it is depending on area, it is depending on theta. We call this flux. So then the formula becomes E induced is minus d phi by dt, where flux is given by n into integral B dot dA. N is the number of turns. And here the negative sign indicates opposition. We will see what is that. This was the Faraday's law of electromagnetic induction. So if I try to write this in terms of statement, I'll write down here. That only what the statement. The EMF induced in a loop is proportional to rate of change of magnetic flux. Now this you figure out from a lot of experiments. And Faraday has no clue why this is happening. The same way we have no clue why gravitation comes because of mass. Like I keep saying, we know how things work. We don't know why they work. This Zoom, they changed all those options, I guess. How do I share my screen, right? Where is this? Weird. I can't find this option. Anyone can tell me where can I find this?
Maybe it'll be there under that.
I was seeing there also. I couldn't find this. Pura Naya, I think I got a new version, I guess. This thing looks so messed up. I need to find out. Yeah, I got it. I need to give an option, I guess. You can see?
Yes.
Okay. Yes, you can see. So let's look at this. Where are you? Yep.
The magnetic induction with an experiment similar to the one that we prepared. I have here, and I have 3 coils. The coil with 1 loop, 10 loops, and 100 loops. I also
The audio is coming, right? Audio is there? No, audio is not coming. Yeah, I need to do something about this thing. Okay, anyways, just look at for this thing.
to the end.
So there we can see that. So we have a one coil, we have big coils and a lot of turns. So basically, if you have more turns, you'll get more flux. You can see he's taking a magnet and he's trying to push through the coil. There's a very small deflection you can't see actually. Now you take a bigger coil, so more turns. If there are 100 turns, then the flux will be 100 times into rate of change. Now you can see a little more. So there, that's your coil. You connect it to an ammeter. Now you took a magnet. There, can you see the needle deflecting? And see, when you're going inside, the needle is going one way. When you come outside, the needle comes in the other direction. And the faster you move, the more it deflects. Now, if you take the slower you go, so it doesn't change much faster. Now take a bigger coil. Now this is like almost I think 1,000 turns or something. So here you'll see more deflection even for small changes. Now see, can you see how big the needle is deflecting? Now we have no idea why this happens, but it is happening. Clear, everyone? Now this you can do even better. You can go to that Colorado website which I gave you before. Look at this thing. So there we have a coil there and we have a magnet here. So if I go slowly towards this, you can see the bulb is glowing. So, but if I go fast, you can see it glows much more. I think if I show the field lines, there you can see the field lines are crossing. So in this case, I'm moving the magnet. If I take another case, look at this thing. This is cool. This is a generator. So here I'm putting water here and that magnet is rotating. So you can see that. So this thing is rotating. So here you're changing the angle. This is an AC generator basically. This is how we actually create electricity. So here you can see the field lines there. You can have more loops. You can see the bulb will glow much more brighter. You can increase the loop area. That is a field meter. Okay, this is the compass needles. So that way. Clear? So there. So that is the proof I can give you. Like if you ask me, sir, how does Faraday know? Why are you getting this? This is the thing. Clear with this? Next thing, Lenz's law. So it is based on that minus only. I think I had an update, unnecessarily updated it. I have to again sit and figure it out. Anyways. So what the Lenz's law says is the current or the EMF induced is induced in such a way. Listen, this is important. If you understood this, I think you'll get the directions. In such a way to oppose the change in flux. This is how normal nature works. If something is trying to increase inertia, basically, you try to decrease it. And you will see what happens if it is not. So what this thing is trying to say is, if flux is increasing, see, I don't have a problem with flux. I have a problem with changing flux. So don't get confused, but both of them are completely different. If flux is increasing, system tries to decrease it. If flux is decreasing, system will try to increase it. The system has nothing to do, like it will try to increase or decrease. Only thing I don't want you to change. If flux is decreasing, system tries to increase it. Let's take an example that you will understand better. Listen carefully. Let's say we have a coil here. Let the magnetic field be B is equal to B naught into T. T is the time. Let the coil ka radius be A. Now, what is the flux? Flux is equal to B naught into time into area pi A square. What is the EMF? I'll just take the magnitude. d phi by dt. We are not including the minus sign. This will be B naught into pi A square. There. I got the EMF here. Now the confusion is, when I took this EMF, how is the battery? Is the battery like this, plus minus sending current this way? Is the battery like this, sending current in the clockwise? Isn't this the confusion? EMF though you got. Now I don't know which way is the direction. Now listen carefully. This is the catch. So we know B external is this way. Let's look at the first case. In the first case, if the current flows anti-clockwise, how will the magnetic field be? This will create the field in this direction, B induced. Agreed? In the second case, if the current goes clockwise, the B induced also will be into the plane. And B external is also into the plane. So let's look at the second case. What happens? So in the second case, the net field will be B external plus B induced. That means whenever the current flows, it will actually increase the magnetic field. Therefore, if I increases, this will increase the B induced. B induced increases. If B induced increases, then B net increases. If B net increases, then flux increases. If flux increases, EMF increases. If EMF increases, current increases. Can you see what happened? This is called a positive feedback loop. Such things are called positive feedback loop, and eventually current will go up to infinity. Eventually current will tend to infinity. This system is feeding itself. The system is just making it go off. Now the question is simple. Where are you getting all this energy from? Getting it, these kind of systems will blow off to infinity. You get infinite energy. It doesn't make sense. These kind of systems, right, are called positive feedback loops. Basically, they're unstable. Positive feedback, meaning whatever output you give, that itself is increasing your input, and your input increases the output increases the input, and so on. This is a positive feedback. These systems don't exist in nature because eventually they'll blow off to infinity. So this is not possible, because in this system you'll get infinite energy, isn't it? If you have infinite current, I can produce infinite heat in the resistor. So this is wrong. But look at the first part. In the first one, if you see, the B net will become B external minus B induced. So here flux is increasing. So I need to decrease it. So here B induced decreases B net. Therefore flux decreases. These kind of systems are called negative feedback loops. This is a full course in mechanical engineering. All mechanical systems, right? When you make robots or when you make fighter planes or anything, there's all negative feedback loops. Clear with the steps? Let's do one or two examples and then we will do it in more detail in the next class. But everyone got the idea? See, there's only two directions, clockwise, anti-clockwise, isn't it? Har bar wahi confusion hai. In one direction, you'll support the system. In one direction, you'll oppose the system. So you need to ask yourself what to do. Example, let's say we have an infinite current loop. Let's say we have the square loop here. This is going this way. Can you tell me the direction of the current, clockwise or anti-clockwise? That square loop is going towards that infinite wire. I'll give you steps how to calculate late next class, but how do you do this? Clockwise, anti-clockwise. Listen, I'll show you one. Step one, what is the external field ka direction? This is B external. Agreed? That is step one. We will write that in the next class. So this is B external. Fair enough. Second, if you get closer to the loop, what is happening to the flux? If you get closer to this thing, flux increases. Great. So what should you do? Therefore, we should oppose. Who will oppose? The B induced. Therefore, B induced must be opposite to B external. That means B induced is which way? Up. If B induced is up, use right hand thumb rule. The thumb should be out of the plane. The fingers will give you the current. So what is the direction of the current? Anti-clockwise. Is the logic making sense? Are you getting the steps? Step one, find the direction of external field. Step two, decide whether the flux is increasing or decreasing. Step three, since here it is decreasing, I need decreasing, I need to increasing, I need to oppose it. Matlab B induced and B external are opposite. So put your thumb in the direction of B induced, the fingers will give you the current. Easy? Can you tell about this guy? Let me give you one more example. Now it's going this way. This is going this way. Step one, B external ka direction out of the plane. It is getting closer to the wire. Flux is increasing. Therefore, B induced must be opposite. So put your thumb into the paper and rotate clockwise. Make sense? What about the next one? This thing is going parallel to the wire. Step one, B external is inside. Step two, flux is constant. Story ho gaya. Current is 0. Steps are clear. We will write that more formally in the next class. So that is the basic. So if you understood till here, this will give you the magnitude d phi by dt. Lenz law will give you the direction. You know how to find EMF. That will be the first part in the chapter. So that we will deal with on Friday. So Friday when we catch up, we will do more problems on this. We have some pretty good ones, and then we will see even motional EMF part also. Let's see how it goes. Okay, so with that, we'll wrap up for the day. So any doubts in today's class? Anything else you can stay back and ask, or else we'll see you on Friday as usual. So take care, stay safe.